We have a concentric cylinder and see how it is kept. Here it's a rim of different K's. The center one is K, the other one is K, 2K. Whatever is written, I have to see what they have given it as. Now, the radius is R and the radius is 2R. I'm just showing you if the cylinder is kept like this, then this area has to be taken. Let's solve for the inner part. I'm shading inner part like this, and its area is pi r square. So I'm writing dq by dt for the inner part. Okay, what is it? K area pi r square, T1 minus T2 divided by L, and T1. So I've written like this. See, L upon K1 pi r square. Okay, this is K1, this is K2. So no, it's not given like K1, K2. Okay, it's K1 and K2 only because see the end result is in K1, K2 only. So I've written like this, L upon K1 pi r square. You understand why I'm writing like this? You understand why I have brought it down? I'm only writing in the form of Ohm's law, delta T by R thermal. That way I'm writing. Now for outer, K pi 2R square minus, because outer is only this much, inner is different material. So I have to calculate the area of the rim. I've written here area of the rim, T1 minus T2 divided by L. Now, so dq out is 3 pi r square. Can you see that? It is 4 minus 1, 3. 3 pi r square K, T1 minus T2, which is T1 minus T2 upon the same thing I've done here as well. Now, inner I've got L upon K1 pi r square, and the outer part I've got L upon K2 3 pi r square. So now I'm going to solve the resistances. How we solve it? 1 upon R is 1 upon R1 plus 1 upon R2. So when I write 1 upon R, I simply reverse it. So it will become K1 pi r square by L. As you can see, reverse it. And this is K2 3 pi r square by L. So pi r square by L I've taken common. I get K1 plus 3K2. So R thermal I've got L upon pi r square. I'll again reverse because this was R 1 upon R thermal. To get R thermal I have to reverse it again. Take it up. So we have L upon pi r square K1 plus 3K2. This is the first equation. Now for equivalent heat, because I have to calculate the equivalent thermal conductivity, if I take a single cylinder, what should be the value of the K so that it transfers the heat in same time? That is the meaning of equivalent thermal conductivity. Now, if there is a cylinder of single K, for that, how what will you write? It's a single K, na? Then you have to take the radius as 2R. For that, you will write T1 minus T2 because temperature is not changed. L is the length is not changed. Only the area is written because it's a whole single block. So L upon Ka, okay, for pi r square. By for pi r square because it is pi 2r whole square. Don't consider I have taken a sphere, pi 2r whole square because the radius is 2r for this. So we get R thermal as L upon 4 pi r square. Now we have two formulas. One is this for thermal resistances. And since I have to find out the equivalent thermal conductivity, these two should be equal. So when I put 1 equal to 2, what do I get? See, one is L upon pi r square K1 plus 3K2 and the other one is L upon 4 pi K r square. Little bit calculation is there in the question, but I think you have understood. When I equate the two, what do I get? L upon pi r square, L upon pi r square gets cancelled. So K is equals to K1 plus 3K2 divided by 4. That is the correct answer.